And like I said, that's the least inclusive definition. Then we have the Bronsted-Lowry definition. And a Bronsted-Lowry acid donates a proton, a base accepts a proton. This is slightly more inclusive definition, but the most inclusive definition is this Lewis acid and base definition. But it also is a little bit more complicated in recognizing what's happening because we have to look at the flow of electrons. So a Lewis acid accepts an electron pair, a Lewis base donates an electron pair. We form covalent bonds between usually a proton and something else, but it doesn't have to be. So we looked at an example with, I believe, ammonia and BH3. That one's in your textbook, I believe. So again, Lewis acid definition, you need to draw your Lewis structures in order to see this happening. Spend some time with this Lewis definition. Like I said, it is the more complicated one. It's probably the least pleasing to spend time on, but it does show up in homework and exams and things like that. I mentioned you need to know your strong acids and bases. Yeah. Oh, and I don't like that one. H2SO4. H2SO4 is tricky. I'll tell you why. Okay, I'm going to just kind of go ahead here. We talked about conjugate acids and bases. Here we have ammonia reacting with water in equilibrium with the ammonium ion and hydroxide ion. In this case, ammonia acts as a base, or is a base. Water acts as the acid. We form ammonium ion, so that's our conjugate acid. And hydroxide is the conjugate base. Hopefully you're feeling some comfort with conjugate acid-base pairs. It's important to recognize those. So the next thing we're going to talk about is the pH, calculating pH, and a little bit about the pH scale. So calculating pH is really just reporting the H+ concentration in a different way. And we use the definition that pH is equal to minus the log of H+, or we want to write it with our hydronium ion, minus the log of H3O+. Okay, again, we're, for the sake of this class, we're going to use H+ and H3O+ concentrations as equivalent. If we are looking at pure water at 25 degrees Celsius, what we find is that the H+ concentration is 1 times 10 to the minus 7 moles per liter. And so to calculate the pH of that, you probably recognize that the pH of pure water at 25 C is 7, but that's minus the log of 1 times 10 to the minus 7. And in terms of significant figures, this is like the one rule that I can actually remember for sig figs. I don't know why. I guess I calculate pH relatively large amount with all my classes. But so the rule is that in the answer of the log, so that's what we're going to come up with here for pH, only the digits after the decimal place are significant. So when we calculate minus the log of 1 times 10 to the minus 7, we're going to end up with 7. That 7 is not significant. That's basically the number that's in the power here. And then so the other significant figures come from what we're multiplying that by. So there's 2 significant figures in 1.0, and so we have 2 significant figures in the digits after the decimal place in the pH. So only these digits are significant. Okay? So we have 2 sig figs here, and we have 2 sig figs here. Okay, that one's a little bit confusing, I think. 7 doesn't count. Whatever before the decimal doesn't count. Have you done that in lab? No? Yes? No? About to? Okay. The other way that we can think about concentrations is with POH. Turn off my phone, jeez. So again, P, lowercase p in this is just standing for minus the log. So we can do P whatever and just take minus the log of whatever that value is, okay? And we're going to do that repeatedly through the weak acid-base equilibria chapters. So POH is equal to minus the log of the hydroxide ion concentration. Again, pure water, 25 degrees Celsius, has an OH minus concentration of 1 times 10 to the minus 7, and so the POH is equal to 7.00. Same calculation, same numbers. The reason that pH and POH are the same, and that the H plus concentration and the OH minus concentration are the same for pure water at 25 degrees Celsius is this Kw that we saw last time. Kw is equal to the concentration of H plus times OH minus, which is equal to 1 times 10 to the minus 14 at 25 C. So when I'm solving for H plus and OH minus, I'm taking the square root of 1 times 10 to the minus 14. That's where those values are coming from. Does that make sense? So here's our relationship between H plus and OH minus. To calculate an H plus concentration, if we rearrange this equation, we will have the concentration of H plus is equal to the concentration of OH minus. Kw, divided by the concentration of OH minus. And then the concentration of OH minus is equal to Kw over the H plus concentration. So we should be able to pretty easily convert between H plus concentrations and OH minus concentrations using Kw. Okay? There is a somewhat, now look, I've put in H3O plus here, same thing. Okay? So there is another convenient way of expressing this Kw expression, and that is by taking minus the log of both sides. And so we'll get minus the log of Kw equals minus the log of H3O plus times OH minus. And I said minus the log of anything is just P anything. So pKw is equal to, we got to follow our rules for logs here, minus the log of H3O plus minus the log of OH minus, because when we're multiplying things together inside the log, it's the same as taking them outside, doing log of both, but adding them together. And so we end up with pKw equals pH plus POH. And at 25 degrees Celsius, we know that Kw is 1 times 10 to the minus 14. And so pKw is equal to 14. So if we want to sort of simplify this equation even more, make it very user-friendly, at 25 degrees Celsius, 14 is equal to the pH plus the POH. And now, if you have a pH and you want to determine the POH, you could easily convert between those using this equation. Questions on that? Okay. So let's practice some. On the left-hand side, I've given you an H plus concentration and want you to calculate pH, POH, and OH minus concentrations. You can do this in any order that you'd like. And on the right-hand side, I've given you pH and want you to calculate the other three things. So take some time and do that. We'll just take a couple minutes on this. I will give you the answers if you don't complete all of them, and you can check your work. All right. So hopefully you've worked through a couple of these. So to find, let's work on the left-hand side here. So to find pH from our H plus concentration, I'm going to take minus the log of the concentration given. How many significant figures are in that digit, that number? 2, right? Yep. Cool. And so we'll have 2 sig figs after the decimal. I end up with 4.82. Is that what you all got? Yeah. So for POH, that's the next thing I did. You could go from, well, I think that makes the most sense. So we'll do POH is equal to 14 minus the pH. And so that's 14 minus 4.82. And I get 9.18. Good. For OH minus, we could use our OH minus concentration is equal to Kw over the concentration of H plus. Or we could do the inverse log, which I guess I haven't shown. If we do 10 to the POH, 10 to the minus POH, let me get that, let me move that over. If we do 10 to the minus POH, we can end up with the OH minus concentration. So using this expression. So in order to get rid of the log, I've taken the minus sign, divided both sides by -1 to move the minus sign over to the POH side. Now I have 10 to the log of OH minus, so that's going to give me OH minus. So 10 to the minus POH, so 10 to the minus 9.18, is going to give me the OH minus concentration. And so for that, I get 6.6 times 10 to the minus 10. Again, the other way you could do that is with this expression. Kw over H plus. So you have 1 times 10 to the minus 14 over, well, I'll leave all the zeros. 0.000015. Everyone okay with that? When I'm going from pH to H plus concentration, I find it easiest to use this equation. So just in general, concentration of H plus is equal to 10 to the minus pH. Does that make sense? Yeah. So the sig figs on the OH minus concentration. So when we have, if I use this calculation, I have 9.18 as my POH. That only has 2 sig figs. And so this answer should only have 2 sig figs. Yep. It's tricky. Okay, other questions? Okay. Instead of going through the others, I'll give you some answers here. So when we have pH of 11.51, our H plus concentration, I get 3.1 times 10 to the minus 12 molar. OH minus concentration should be much higher, right? We have a high pH, so we have a lot of hydroxide. So we have 3.2 times 10 to the minus 3. And the POH should be 2.49. Too small to see. Questions on any of those calculations? These should be pretty quick, pretty fluent for you. So if they're feeling a little bit tricky, make sure you practice these, and so you can get kind of quick at them. Okay. Write it out very nice. Okay. We talked a little bit about the autoionization of water. So water can react with itself to form H3O plus and OH minus. And this is where we get our Kw expression, right? So Kw is equal to H3O plus times OH minus. And recall, we don't include liquids in our equilibrium constant expression, so that's why there's no water here in the denominator. The H3O plus and OH minus, those are aqueous, so they get included. So when we're thinking about adding acids and bases to water, we are altering this equilibrium. Okay? If you add a weak acid to water, it itself is going to have an equilibrium, and that's going to be the main thing that we care about. But if we're thinking about a complete picture, this is always happening in water. And so we kind of sometimes need to think about this equilibrium as well. So if we add more H3O plus to the solution, which way does the reaction shift to regain equilibrium? Towards the reactants or products? Towards the reactants, great. And so what happens to the OH minus concentration? It decreases, yeah. So that's one thing to keep in mind when we're thinking about addition of acid. We're effectively making this equilibrium shift towards the reactant side, reducing OH minus concentrations here. Let's see. I think I need the slide. Okay. If we add a strong acid to water, so a strong acid is always going to completely ionize in solution or completely dissociate. Okay. Just like a salt, completely dissociates. So if we put HCl in solution, I'm going to use single reaction arrow to show that this happens to completion. We form H plus and Cl minus. And that's not all that interesting, really. I guess where do I want to go with this? So because we're adding H plus or H3O plus to our solution, and because our autoionization of water happens to such a small extent, again, thinking about H plus and H3O plus as interchangeable, when we add a strong acid to water, we don't really need to consider this equilibrium of the autoionization of water, as long as this strong acid concentration is high. Because what is the concentration of H3O plus from the autoionization of water? It's 1 times 10 to the minus 7 molar. Right? If we add anything greater than 1 times 10 to the minus, I believe it's 6 moles per liter of acid, then we don't need to consider the equilibrium with water. If you take analytical chemistry, that's not always the case, and we show you how to deal with a strong acid where the concentration is so low that you end up with needing to account for this equilibrium. So here's a quick calculation to show what I mean. All right? pH. What is the pH of pure water at 25 degrees Celsius? 7. What's the pH of HCl, of a solution of HCl when the concentration of HCl is 1 times 10 to the minus 8 molar? Calculate that real quick for me. Who wants to tell me what you got? Yeah. 8. Does that make sense? It's the right number, but it doesn't make sense, right? Because that would be a basic solution, but we've added HCl. And so when the concentration of the strong acid is low enough, we actually need to consider this equilibrium. You aren't really going to see problems where that happens, but I think it's kind of interesting to think about, where you can add acid and be able to actually calculate that you've created a base. It's the falsehood, but that's because there's another equilibrium that's taking place. Okay, so let's go back to sort of where we expect you to be. If we add, if we have a solution that is 0.1 moles per liter HCl, how much H3O plus is formed? H3O plus is fine. Go ahead. 0.1 molar, right? So for every HCl that you put in solution, you get an H plus, which we are considering to be H plus, right? Okay. If we also consider that autoionization of water, that concentration is going to be actually less than 1 times 10 to the minus 7, okay? So we're going to ignore that. Okay, so what is the pH of a solution of 0.1 molar HCl? Here we go, we're re-summarizing again. If we calculate the pH, pH equals minus the log of 0.1, we end up with 1.00, okay? What's the pOH? 13. Okay? So I guess one takeaway from this is that for strong acids and bases, the pH calculations should be very quick. Okay? And that's why I told you to memorize your strong acids and bases. So if you put a strong acid in solution, however many protons are on that strong acid, that's how many are formed in solution. That's the concentration that goes inside the log for the pH. Okay? On your strong acid list, how many diprotic acids are there? I can't remember. Is there only one? Yes. H2. SO4 is tricky because only that first deprotonation is strong. You can end up with HSO4 minus, and that losing that second proton is actually a weak acid. So that's not a great example. But let's look at a base then. So barium hydroxide is a strong base. Okay. Let's say we put 0.1077 moles of barium hydroxide in 1 liter of water. We're basically making a saturated solution. Let's first calculate concentration of OH minus. Okay. So that's just a chapter 13 problem, right? Concentration of OH minus when we put barium hydroxide in solution. Work on that quickly here. Notice I'm writing some things. Okay. With barium hydroxide, for every 1 mole of barium hydroxide that you put in solution, you end up with 2 moles of hydroxide. All right, see the subscript 2? So this is one of those places where it's really easy to be working quickly, and you miss this, and you would automatically say, oh, it's 0.1077 moles per liter. It's not. It's 2 times that, okay? So we calculate our number of moles. We end up with 0.2154 moles of hydroxide. And so, as we said, this was dissolved in 1 liter of water. And so we end up with 0.2154 moles per liter. Everyone okay with that? So barium hydroxide, calcium hydroxide, strontium hydroxide. Those are your 3 strong bases where for every 1 you put in solution, you get 2 hydroxides. So keep an eye out for those. Okay? So once we have our hydroxide ion concentration, we can calculate the pOH. So the pOH is going to be minus the log of 0.2154 moles per liter. And I get 0.6667. 1, 2, 3, 4, yes. Okay. pOH is low, that means it's strongly basic. This is a strong base, so that makes sense. If we calculate the pH, do 14 minus that value, I get 13.3332. Everyone okay with that? Okay. The next part is sort of like what happens if you dilute this solution. So if we start with our 0.2154 moles per liter, and we add 500 milliliters, what happens to the pH? And so basically, to calculate this, we're going to use the number of moles that we started with and divide it by the new volume, which is 1.5 liters now. I think I'm missing a sig fig there, but I kind of don't care right now. And so we'll end up with 0.2154 moles over 1.5 liters. And the new concentration is 0.1436 moles per liter. From here you can calculate pOH. And then calculate pH. And I get 13.1572. So the pH doesn't change very much. It's a strong base. Questions on that? Okay.
It's like a 3 something.
Yeah. You guys want to do one, or is this too easy? Calculating the pH. Is it boring? All right. I'm going to give you the answer and we'll move on. Because we have a lot to do. Should get, once you do this, take your time and do this at home, you should get 3.1 times 10 to the minus 7 molar. Okay. Let's do something a bit more tricky. Here we have a hydroxide ion concentration of a solution. It's 1.5 times 10 to the minus 4 molar. What is the pH? So let's take a minute and a half and solve this problem. You can work with your neighbors. All right. How do these calculations feel? Everyone, who's good? Who feels good with these? Good. I'm getting thumbs up. Excellent. All right. So if our hydroxide ion concentration is 1.5 times 10 to the minus 4, I went ahead and calculated POH first, but that's not necessarily the way you have to do that. Get 3.82, and then from there calculate the pH and get 10.18. Questions on that? Okay. Here's sort of a weird problem. I can't remember why I chose this. It must show up in the homework or something. It's not something I would have written. We were taking two strong acids and mixing them together and then calculating the pH of that mixture. So the approach to this type of problem is we're going to find, hang on y'all, we're going to find moles of H plus from HCl. Then we're going to find moles of H plus from HI. And then we're going to add the moles together. Find the total volume. Find the molarity. It's a lot of steps, but I'm really exaggerating it here. And once we have the molarity of H plus, from there we can calculate the pH. Okay. So again, two strong acids. I think it's important to note that if you mix two strong acids, they don't react together. Like, they're just hanging out in the solution. But maybe they make H plus, they make their counter ions, they make their conjugate bases, Cl minus, H minus, Cl minus and I minus in this case. Should we work it? Or do you guys feel like you could do this at home? Work it? All right. Okay, so let's take, from our HCl, we have, what is it? Yes, 0.020 moles per liter of HCl. For every, and I'm going to write this out because that, like the barium hydroxides, that'll get you. So for every 1 mole of HCl, you get 1 mole of H plus. Okay, maybe you recognize that right away, but sometimes it's useful to be incredibly deliberate. So for our 1 mole of H plus, okay, so we end up with moles of H plus, and we have 50 milliliters of that. So we still have liters in the denominator. You can't see where I'm pointing. You have liters in the denominator for my moles per liter. I'm going to multiply by the volume to get moles of H plus. And so that's by 0.05 liters. So I converted my 50 milliliters to liters. So now liters are going to cancel. Moles of HCl cancel. I'm left with moles of H plus. And I get 1 times 10 to the minus 3. Okay. Same thing for HI. I'll do the same calculation. We have 0.010 moles per liter. HI. For every 1 mole of HI, we get 1 mole of H plus. And by our volume, we used 125 milliliters of the HI solution, or 0.125 liters. And so I get 1.25 times 10 to the minus 3 moles. So I said we can just add up these moles. We're just making H plus. We want to calculate the total concentration of H plus in solution, so we can add these up. And we end up with 2.25 times 10 to the minus 3 moles. And in step 4, we're going to find our total volume. So we mixed 125 milliliters of the one solution with 50 milliliters of the other. So our total volume is 175 milliliters, or 0.175 liters. So to find the molarity of H+, we're going to have 2.25 times 10 to the minus 3 moles. That's our total moles, divided by our total volume, 0.175 liters. And we get 0.0129 moles per liter. pH is equal to minus the log of that value. And I end up with 1.889. And if it's not acidic, you've made a mistake. So kind of a lot of steps, but basically taking two acidic solutions, finding the total proton, H+ concentration, using that in our pH equation. You can do the same if you mixed two bases together, find OH minus. If you want to find POH, you could calculate that, etc. Questions on that? Okay. Now, I definitely want to introduce here the concept of weak acids. Okay. So, strong acids completely ionize in solutions. By definition, weak acids do not completely ionize in solution. And so we have an equilibrium present. So this is all of our chapter 15 material. Now we're applying it to acids and bases. So here, this is acetic acid. I'm giving away the questions here, I don't care. This is acetic acid. It's going to react with water as a base to form the conjugate base, which is acetate ion, and H3O+. Okay. Again, note the equilibrium arrows. That says it just doesn't dissociate completely. So I think I have this spelled out a little bit more on the next slide. For our weak acids, we will always find a Ka less than 1. So we expect the reaction to be reactant favored. So that means that the dissociation does not happen to a great extent, right? And so, for example, for acetic acid, if we put 0.1 moles per liter of acetic acid, in solution, we only get 1% of acetate ion formed. So only 1% ionizes at that concentration. So again, very weak acids, or actually even acetic acid is not that weak of an acid, but even that doesn't ionize completely to any large extent. So if we look at what that means in terms of picture, so if you're trying to imagine what the solution might look like, on the left-hand side, I don't know, whichever one this is, we have a strong acid. The molecules completely dissociate. And so if we're looking at a molecular level picture, we've produced the conjugate base, which are the green spheres with a minus charge, and the H3O+ hydronium ion. And you'll find that there are no HA or strong acid left in solution. If we have a similar picture for our weak acid, you'll notice that we have formed one conjugate base, A-, and one H3O+, just for example. And then the remaining molecules are the HA molecule. Okay. You have a list of weak acids. I mentioned there was a quiz, like one of those trivia quizzes on Carmen, a link to that from Friday, including some of the weak acids, and we'll include, I think, a good number of the ones shown here, but not all of these. But the main thing just to learn from this table is that we have different values of Ka. So this is going to be a new equilibrium constant that we're going to show you. Ka refers, just like what you would expect, it's now for the equilibrium constant specifically for a weak acid. The larger the value of Ka, the more dissociation happens, or more ionization. The smaller value of K, less ionization. And if we think about what that means in terms of the strength of the acid, larger Ka value, stronger acid. Smaller Ka, weaker acid. We don't have K values for our strong acids and bases because there is no equilibrium. If you're wondering about that. Okay. We also have some diprotic acids. H2SO4 is on your list of strong acids. First deprotonation, it ionizes completely to form HSO4 minus and H plus, everything aqueous. That HSO4 minus, though, as I mentioned, has an equilibrium associated with it. So HSO4 minus in solution can form SO4 2 minus and H plus, but note the equilibrium areas, okay? HSO4 minus is a weak acid. We have carbonic acid, H2CO3. Oh, I forget the name of this. Doesn't matter. H2CrO4. There are many other diprotic acids. Triprotic acids, phosphoric acid is a common one that you may even use that in lab for various things. Okay. Oxalic acid is another weak acid that is diprotic. It has two K values associated with it. The first one for losing that first proton. If we write it out in general, we'll have H2A forming HA minus plus A minus. That's not right. HA plus. A moment. Okay, so in any case, what this diagram is showing you is these values of Ka, okay? So in this figure, the purple with the two white spheres are representing the fully protonated oxalic acid. To a certain extent, we will form the HA molecule, and then couldn't even draw the right number of oxalic acids to form one single fully deprotonated form. So there's 1/10 of one shown. That's basically what I'm trying to show you is that for diprotic acid, Ka1, losing that first proton is always larger than the Ka for losing the second proton. And it's very unlikely that losing a second proton will have any effect on your pH because it's just so small in comparison. Okay. So we're thinking about what do weak acids react with water to form. So I like to write every weak acid as an HA. Okay, monoprotic weak acid, HA. If we allow it to react with water and have an equilibrium, it's going to form H3O plus and A minus. Okay. Oftentimes we'll see weak bases written as B, I guess for base. They react with water to form a protonated species, BH plus for instance, and hydroxide. So note the difference. A weak acid reacts with water to form acid, H3O plus. A weak base reacts with water to form base, OH minus. Okay. But again, equilibrium arrows, ionization does not occur completely. And so when we want to calculate equilibrium concentrations, we get to use ice tables. And that is where we will start next time. Have a good day, everyone.
So like if a problem like asks you to so basically for calculating the pH, are you like supposed to like round it and then each afterwards? So like because there's a difference between like so this is me calculating pH, and if I use the rounded number, it gives you a different decimal digits. Like versus if you were to use the actual data.
Yeah, you're right.
Yeah, it's one of the homework problems. I was just not. I didn't want it to be inside of that. So.
Oh,
But it's
I would probably round at the end, so using that
one.
That one, yeah.
Gotcha. Okay.
Yep.
Thank you.
Good luck. Okay.
What's it do here?
Okay.
I thought it was like 10 to the negative log.
It is. Yeah.
But whenever I plug it in, I always get like some big numbers, like really
Okay.
large numbers.
Let's try it.
Of course, I can literally.
Have a good day. See you. Oh, it's not minus the log. It is 10 to the minus pH.
Oh.
Here, let me go back to that slide.